Okay, hello, welcome everyone. Thank you for coming early-ish on Sunday morning to the machine learning tutorial. If you don't know, my name is Jenny.
Hey guys, I'm Jenny's assistant, Shivani.
And this will be our machine learning tutorial.
Okay, so let's introduce what machine learning is in the first place. So a really general definition of machine learning is that it's a field of study that basically gives computers the ability to learn without necessarily programming it, like without coding what it's going to do. So we use machine learning like a lot in our daily lives, like companies use it a lot. It's everywhere now. It's an emerging technology. Here are just some like examples of how it's being used. So to rep my team, I put this mass detection example, which is like a very good example of how we're using machine learning in COVID. It uses computer vision to basically determine whether the person in the image is wearing a mask or not. And you can do that with like looking at CT scans, determining if there's a tumor and if it's cancerous or not. Siri uses machine learning, language processing. You can use it to predict economic growth, the market value of houses, and even on Netflix, which we all like use all the time, like recommendation engines, which basically personalize what types of shows to recommend you based on the data they collect by what you watch. So basically, why do we need machine learning? So let's think about how humans, if we had this issue, right, of like we have to determine whether this image is a cat or a dog. So as humans, how would we do this? Like humans, we would, if we were gonna like make our own model, we would extract features from these images, like um, the color of the animal, like the size of the animal, the height, the weight, how many eyes are in the picture, how its ears are shaped, like features that humans as we as humans can recognize. And then we would maybe assign like a weight to these features based on how important we think they are and come up with some sort of like linear or nonlinear model to like connect these weights with the input features and determine like a final value which would say yes, this is a cat, or this is a dog. Let's say we test our model and it's not as accurate as we thought it was. It like failed because like we as humans just don't know like apparently how to identify a cat or a dog using math. But machine learning is where it would be really useful for us. Like, machine learning is useful because like the models, based on the data you gave it, based on the labeled data you gave it, will extract features that humans might not be able to recognize. And it will list those features in terms of which features are the most important for classification. So we can then look at that and then determine which features are actually important and then improve our model. Machine learning will basically do that by training and evaluating data to update which features are important and then eventually identify, in this example, if it's a cat or a dog. So someone said, Tom Mitchell from Carnegie Mellon University once said that a computer program is said to learn from experience E with respect to some task T and some performance measure P if its performance on this task T as measured by P improves with experience E. So this may sound like a lot, but let me make an analogy for us to understand like how models kind of work in like a simpler way. So let's think about them. Let's think about like machine learning models as little children, like preschoolers, learning how to identify shapes. So on a child's first try, right, it has zero experience. So it may correctly identify a circle. It may get all the circle and the triangle and the square wrong. It may do everything wrong, but they still gain some experience from that period, right? From that the first data they receive, they still gain some experience. And they'll use that experience when performing their second task and then measuring that performance. And then with each task, they gain some experience. So after 100 tries, right, you expect the child to be able to identify a circle correctly, a triangle correctly, and a square correctly. So they're basically optimizing their performance P based on all the gained experiences, all the learned experiences that they gained over the training process. So machine learning models work in like analogously, I don't know if that's a word, in a similar way. So there's the main branches of machine learning, or you can classify it as kind of like supervised learning or unsupervised learning. Supervised learning is basically when we predict based on some data that we're given a class for that data or like a value or a label for that data based on data that we're given that's pre-labeled. So like if we look at like the image that I have on the side, an example of supervised learning is that if you give me like a bunch of animals, right? And I want to classify whether it's like a duck or not a duck. That would be supervised learning if the data I have provided says like gives me a picture of a duck with a duck, a picture of a rabbit, and it's not a duck. For example, like all my data is pre-labeled. So then my algorithm can train on that data, test whether like they got it right, and then update like their model so that they can determine whether it is a duck or not a duck. So different methods of supervised learning are classification. We use that in like image classification. More complicated is like image captioning, where we look at an image, determine what's in it, and like write a caption on it or something like that. There's also regression, which, as I said earlier, some examples are like predicting stock prices based on like previous like company stock data, predicting real estate value based on current data, and etc. And then the other branch we want to talk about is unsupervised learning, which the difference between supervised learning is that the data we take in is unlabeled. So we basically just feed a bunch of data into our model, and the model will determine, based on how you like construct it, will determine certain patterns or groupings in the data. So to continue the analogy of this duck and not duck stuff, in the unsupervised learning thing, like instead of classifying it as duck or not duck, the algorithm would kind of cluster it based on these are ducks, these are rabbits, these are, I can't see that other animal, but whatever that is, like basically clustering the data and finding patterns in it. So that's also useful depending on what you're trying to accomplish. Hedgehog, thank you. So before we kind of go into what we're doing today, we want to talk about linear regression. And linear regression is something we may have seen in like AP stats or something you can do on your graphing calculator really easily. But like the base concepts of it are like the introduction to what a neural network, which we'll talk about later, does. So linear regression basically is a statistical approach that will kind of model a relationship between input features and the output. So like if we think of like a line, right, like y equals mx plus b, like a feature that we would update is like the m, like the slope, and the b, like m and b would be variables that we would have to update through using our linear regression. So like here we can also do like multiple variable linear regression, which is just if you have like multiple features and multiple coefficients that we linearly compute to find the output value. So the idea behind this is to lower the cost while maximizing performance. So later on, we'll talk about like the cost function, the loss function, sometimes it's referred to as that. So in linear regression, we may have come across this already, but the cost function is the least squares function. So the least squares function is basically like, so y prime over there is our model. So like, let's say we come up with some m and b, like some y equals mx plus b, where we determine the m and b. That our mx plus b would be the y prime, and then the actual y for that x would be the y over there. So least squares basically calculates the sum of all these differences squared, and we want to minimize that cost to get the optimal linear regression model. The same idea will kind of continue later when we're looking at neural networks. So like I said before, neural networks, you can think of it as like a really long, way more complicated than linear function that takes in input values and produces output values. So unlike linear regression where there's like, it's linear, neural networks have a bunch of nodes and hidden layers that are all connected to each other. So at this point, like we know what goes into the input layer and we know what comes out of the output layer. We have no idea what features are being recorded and like actually passed on as important information through the hidden layers. So this is when it gets kind of complicated because we almost don't know what's going on. Like when the layers get large and they're very interconnected and we have a lot of deep, it's a really deep model, we don't know what's going on. But the basic abstract idea is that there's weights between each of the nodes. And then when we train the neural network, we pass through, evaluate it, and then update the weights basically. So like after doing that several times, you optimize your model and then you ultimately you minimize this cost function, whatever it is for the neural network. An example of that, oh, it's okay. But an example of that is like what you would use is the same thing I was saying earlier. If you have a picture with a dress, identifying the output would be like, is it a dress? Is it not a dress? So some important machine learning components are things you like steps you want to follow in machine learning is first data preprocessing and feature extraction. So this is like, if I go back to the cat and dog example, like what features do I want to look at? Like what features do I want to input into my model? Like color, height, size, weight, whatever. And then choosing an algorithm, which is like basically what relationship do we want to determine between our inputs and outputs? Like different algorithms are like linear regression, exponential regression. So like how do we basically want to determine the output? Then a very important part, which is like where the model does most of like the learning, where it actually does the learning is the training. And followed by that, we do the evaluation, which is checking the model's performance. And then we repeat this process like through different passes of like, we pass through the data multiple times to basically, when we train and evaluate, update the weights, like in the neural network, like the weights, which are like the connections between nodes. And once we do that enough and our loss function converges basically, then we know our model is at its best performance. And then we also tune hyperparameters, which is kind of to improve the performance more. And finally, we want to predict, this will be like our final prediction where we input some data and then return some value, like our final value. All right, Jenny.
Okay, so I think we had a kind of a broad overview of how neural networks work, and I will be kind of going over the individual components on a smaller level so you can kind of see how they work more specifically. The smallest unit in a neural network is a neuron, and it's modeled after, like the little neurons in your brain. And basically, it kind of mimics the behavior of a brain neuron in that it takes an input, or like an input pulse, and there's like some sort of adjustment to the input pulse to determine whether you want the neuron to fire or not, right? And so basically how it works here is that you're going to have some input, some weight, some bias, and you could have multiple inputs and multiple weights and multiple biases. You're going to add them together into the summation over here in the cell body. You're going to apply an activation function, and then you're going to get the output that way. Let me kind of explain what it means, like in a more conceptual example. So if you're trying to use a neuron to predict kind of the value of a car, let's say that the two inputs you want is the number of years driven and the number of miles driven, right? And so if you have that, I actually know nothing about cars, but I'm assuming one factor is more important than the other. So maybe the number of years driven is much more important than the number of miles driven, in which case you want to weight one bigger than weight two and not equally. And then the bias I was talking about is going to be in the 10,000 because we're assuming that cars are going to have some kind of base value and they don't like deprecate into just a $0 car. Maybe it does. I actually don't know. One conceptual note to touch upon here is that linear regression can evaluate many factors individually and sum them after, right? But neural networks can weigh the combination of factors, which is why neural networks can be more effective and just can pick up on more nuance than linear regression some of the time. All right, and then I know I mentioned the activation function, which is what happens like at the very last stage after summing everything. And what that does is it takes the value and then like squishes it into some kind of parameter. This could be squishing, it into 0 to 1, -1 to 1, etc. This is for two reasons. One reason is that if the numbers get too big, the calculations are going to be massive and it's just not going to be scalable. Reason number two is that it introduces nonlinearity. All of the, the multiplication and the addition have been very linear, and, real life models aren't quite linear. They don't look like, straight lines all the time. And so with this, it introduces some sort of non-linearity. Okay, and then let's go over kind of what a layer is. A layer conceptually is just you take a lot of neurons and you just like stack them on top of each other and they become a neuron. They become a layer. Each neuron has different weights and different decision-making processes, and then you can feed the inputs in a parallel fashion and then get an output vector. Now, what's interesting about this is that you can stack multiple layers together. This is starting to look like the neural network I'm sure you guys have seen like pictures of before. And this situation, each neuron, like let's say you're over here in the first layer, is going to pass forward the modified value. Like they did some sort of calculation with the weights and the biases, put the activation function, and they're going to give it to the second layer. For the purposes of our tutorial, all of these layers are going to be fully connected, which means that this one is going to pass it to 2, this one will pass it to this one will pass it to this one. It'll be like a fully connected network. And I'm sure like for those people who've like, taken like 170 or 270, like you will know that, the number of calculations that have to be done is like extremely massive, which is why, the activation function, among other factors, are important to consider. One last important layer I want to talk about is the softmax layer, which is the last layer of a neural network. And basically what that's going to do is it's going to take the output of this layer, it's done some math, something on it, and we're going to calculate, and we're going to basically transform that into a probability. So basically, given this image, it's going to say, okay, there's a 95% probability that this is a dog and a 5% probability that this is a cat. And traditionally, this is basically the very, very last layer. So it'd be the output layer right here. Okay, let's attempt to put this all together in our example with our example that we're going to be doing afterwards today. So we're going to have an input image of 28 by 28 pixels, right? And then the input layer is going to be 784 neurons, which is basically just 28 times 28. So each pixel is going to go into a neuron, right? So and each pixel value is a value from 0 to 255, 254, 255, something like that. And then some math is going to be done. It's going to be propagated into the next layer, next layer, and then the softmax layer is going to be applied to make it into a probability. And there's going to be 10 neurons in the output layer. And basically, it's going to be a probability of how likely it is that number. So let's say this neuron over here, I hope you guys can see my mouse, this is 0. Hopefully the probability that, this image is a 0 is going to be low. And the probability in this neuron, somewhere over here, that this image is a 7 is high. And that's how we're going to be able to classify that, yes, this number is a 7, it's not a 2, for instance. And okay, and I'm sure one very valid question you guys have been having is like, this process just seems so random. And like, in some ways that's true because you have to tune the bias and the weights like so specifically to the problem you're working on. Otherwise, it's just going to produce garbage. Like it's just not going to make sense. And it's just going to, you're just going to run random math functions on a number and that's all it's going to be. So how are we going to calculate the biases and the weights? And this is done, and this process is going to be simplified a lot in the next 2 slides, but it's through training basically. So basically, like Shivani talked about earlier, what we really want to do is minimize the cost function, or basically just how terribly wrong we are. Because in a classified data set, let's say we go back to that example of 7, we know that this is a 7. But in the first pass through with the random weights and biases, if it comes out and predicts a 2, we know that we're pretty off. And using these 2 functions that we'll later describe, we can change and modify the biases and the weights so that they're more accurate and they'll be able to actually predict things. So gradient descent, this function will kind of set up a cost function that will tell us how bad our predictions are. Again, just like linear regression. And then the parameters of the cost functions are the weights and biases, the 2 kind of variable factors, and then we should try to minimize the cost of it. So I'm sure you guys are also familiar with these 2 pictures. It's kind of, you can take some sort of derivative, right, to find the maximum here. If it's if it has 1 input, but in reality, it's going to be like some million input drawing that we're going to try and minimize the cost of. And then conceptually, backpropagation is that after we run the network once, we're going to evaluate the network, we're going to see how bad it is, and then we're going to update all the weights and all the biases with the hopes that it'll get better. And then we're going to train the network multiple times, and then we'll be able to hopefully have a trained network with proper biases and weights that are actually going to work in predicting the values correctly. Okay, so that was kind of the end of the PowerPoint. Now we're going to try and move on to our exercise of the day.